we'll start the time series modeling by okay, let's go to the file, edit, forecast series. So we'll open a new this thing, and our intention is to forecast the time series. All right, so for which what we do now, we'll use a data set which is present inside the MATLAB's root. It's a time series data, right? And we'll try to make a prediction. What's going to happen next? Will the machine be able to predict? We'll see. Okay. All right. So let's start with the CLC. Okay, let me run this part at once. All right. So everything is clear. So we load the data. So the data I want to load is called as the chickenpox data set. It's already present, so I don't have to bring it from outside. Just as soon as I enter and I run this part of the code, you see the data comes into picture, right? So there is a data, and you can see the data. It's actually 498 cellular data. Everything is a cell. Okay, it's not a matrix. Okay, there are 498 different values present in this. Okay, you can see, right? Now, what we do, we'll use this data so that we'll see that whether the machine is able to predict. Now you see, it's actually if I look at the type of the data, that is whose, right, it actually belongs to the class cell. Each number is a cell. I don't want that to happen. Okay, I want that to be in an array. So for that reason, now you see data is equal to how to convert cellular data into the array. If you remember, we had discussed this in our basics of MATLAB class. So data, use a curly braces for this. Now you see, when I run this part of the code, right, this 1 into 498 cell will change. Okay, just check this. So this is 1 into 498 double. So now you see, it's a double data. It's the cellular data got converted into double. Right? It's an array now. Okay, fine. Now let me see. Let me visualize, because as you know, right? Is it a time series data? I don't know, right? I want to make sure that it's a time series data. So for that reason, I'll try to visualize first. Okay, so we have to use a figure. Okay, so let us call a function figure, and let's try to figure. It's a simple plot. I want plot of the data, and I want to have x label. So originally the data was collected for something like the number of chickenpox cases in a month of a specific region. That's what is the data. So the x-axis will be months, every month, and the y-axis will be, that is y, will be the number of cases. Okay, number of cases. All right, then we'll give a title to the graph. Not this chickenpox cases. Okay, now let's try to run this part of the code. And let's look at a figure. Okay, so this is what is the monthly chickenpox cases. You can see that it's a time series data. You can see monthly it is changing, correct? So once it reaches peak, then it's a lower value, high, low, etc. It actually is a time series. This kind of data is what we call as a time series data. Okay, where the data collected by varying the time, isn't it? Okay, so we got right. So our next intention is okay. Let us try to cut this data into training and testing. So since it is a time series data, do you remember what we do with the time series data? Anyway, we'll divide into maybe 80-20% or something like that, correct? But you don't have to pick this at random, right? Why don't you pick it at random? Because it's a continuous data. It has to know in the same order, right? How the data is actually generated. In the same order, you have to give the data for a tree, correct? So that's okay, right? So let's directly go to the split up, right? We'll try to split the data. Okay, so number of training data, okay, my number of train is equal to, so I'll go for a lower value, so that is a floor of, right? I don't want the total length, correct? I just want maybe say 80% of my data. Let's try to do that. Okay, so that is 0.8580, no problem. 80% is what is the standard, but for a time series or a forecasting, you can go up to 0.9 also. Okay, let's see with zero point 0.8. If it is not enough, we'll go to the 0.9. Numerical length of the data, whatever is the length of the data, right? You take its 80%, right? So let me write the data train. So training data is equal to, in the data, pick up only the 80%. So that is starting from 1. Sorry, I think I starting from 1, go all the way till the number of train plus 1. Okay, so that's the training data. Remaining will be the testing data. Okay, that is testing data will be equal to, directly start from data of, from which number? From the next number, that is number of train plus 1 all the way till the end will be your testing data. Is that okay? Something which we have similar one we had done earlier. Okay, that's the first thing. After this, okay, let's try to run till here and see what's going to happen. So it comes, and also we can see that on the left side, the training data and the testing data have been created. Correct. So you see 399 data will be used for training, remaining 100 for testing. Out of this 199 new, one of them is the last data from here. So totally 498. Is that okay? All right. What's the next step? If you remember, we need to do a standardization, normalization procedure. Do you remember? Calculating mean value, right? Mean value of the data training. Training data, you calculate its mean value. And also you calculate the standard deviation. Okay. So it's denoted as a sigma. Sigma is equal to STD, standard deviation of the data train. Okay, now you using this mean and the sigma, you try to standardize the data. So data uh, norm. Okay, I'll write normalized. Normalized data is equal to, right? What do you do? What's the equation? The data minus its mean value divided by the standard deviation. Correct? So we'll do that. So that is equal to, what's the data? It's a data uh, tree. Okay, subtract the mean from that. Mean is denoted as mu, and then I am supposed to divide this with the standard deviation. So that is the standardization. Are you okay? Fine. Now you see, for a training data, what is the input and what is the output? You are predicting, right? Predicting the next value. So my exit train is equal to the data train normalized from where to where, starting from the first data till, sorry, yeah, starting from the first data all the way till the end minus 1. Are you okay? Why this is end minus 1? The end value will be a predicted value, correct? Because I have to tell you what the machine should predict. That is white tree. What is a white tree? When I give the first data, you remember the same concept I had explained once earlier. So when I give the first data as input, machine should predict the second value, isn't it? So this is data train normalized. First data is given, start from the second data, go all the way till the end. That is the, okay, this is what is the data that needs to be. Okay, right. In the next part, we will define our networks architecture. Whatever convolutional neural network we want to use, we want to define its architecture. Okay, so that will be, first I need to say how many inputs you have. Input is nothing but one sequence, correct? So number of inputs equal to 1, right? And the number of outputs is also 1. It is going to predict only one value. So number of hidden layers equal to, maybe I'll go to say 250. Let's see. Then I'll go for the layers. How to specify what layers, what are the various layers we want to use, correct? So if you remember, the first layer will be, right, it's a input layer. I have to be specific, more specific, saying that what is my input? My input will be a sequence input, time series data. So sequential, not sequential, it's simply sequence input layer of, what's the size? Size is number of inputs. Right, create a layer of this size first. Followed by that, I'm going to use LSTM. number of hidden layers, so many this thing will, so many hidden layers will come into picture. Then, right, I'm not going to use or repeat these layers, right? I'm just going to use a simple, right, convolutional neural network, not multi-layer. Okay, so only one LSTM layer. So I want to take the output, that means fully connected, right? Number of the rest, number of outputs. Create that. And last layer, what should be the last layer? If you remember, can you guess? I'm not using the network for classification. I'm using it for regression. So what is the last layer when you do a regression? When you use for classification, you'll put as a classification layer. But now I'm trying to do the regression. Now the activation is not required. Okay, so just try to recall what we had done. We had used a regression layer. Okay, remember the prediction algorithm we had written for prediction of the what we call it. I think the prediction of the stock market price, right? That one you remember. Okay, there we had used a similar. Okay, so this is the layers. Let's try to run. See. This number of inputs. Yeah, it's running so far. So let's continue. After the layers, you need to define what is called as the options for training, right? So the function to be used is training options. So normally we'll stick the best one, that is ADAM. Then let's go for maximum number of epochs. I want to restrict that to say 500. I don't want to go beyond. Then I want to define the gradient threshold value. So how much it should be? If you remember, the standard value you can assign is 1. Okay, other values are also possible, but we'll use that. So then next we'll try to define the initial learning rate. So again, you can give anything very small, like maybe I want to begin with 0.00 or 0.005 maybe. Okay, let's see. Then I can also specify how the learning rate should be updated. Okay, so what is the method that can be 0.005 close, then go to the next one. Okay, now let me define the initial learning rate is over. So how the rate should be updated? So that is learn rate CHE schedule. It's piecewise. It's piecewise updation. And then how the learning rate should be reduced or increased, how it should be changed. Okay, so that can be written like this. Learn rate drop period. Right, it should be drop after normally midway. Okay, so I'll write 250. Okay, that is because I have 500 iterations. After 250 iteration, I just want this to be reduced. Okay, then learn rate drop factor. By what factor you want to reduce? Say I want to multiply that learning rate, whatever is defined, by say 0.1 maybe. Okay, I just want to reduce it by this factor, right? So that I get a new learning rate that should be applied after 250 iterations, let's say. Okay, then I want to visualize, so I'll go for uh, robos. I keep it 1, then visualize plots, training progress. Okay, let's check whether this will work. Some mistake. This is initial learning rate. Some spelling mistake or something. Let me. Oh, okay, okay. This is not like this. Okay, now I think. Right. So this is done. Now directly you go for the training process. So training results in a trained neural network. We'll put that into the trained into the variable called met and train network. So what do you pass? X train, expected value is Y train, and pass on these layers, and these are the training options. Okay, now let us run this part of the code and visualize what's going to happen. So we can see that the training started on a single GPU. Okay, so the training is over now. So this is what the output we are going to get, right? So the trained neural network is present inside the variable called network, called net, right? Okay. So our next objective is that I want to go for what is called as the testing part, right? For testing, you see, I want to have the standardized data set for the testing, right? So, okay, I'll go for the testing part from in the next section. So let's see what we are going to do here. So you see here, I'll go for, I think I call by standard, okay, data train normalize. I'll similarly call the data test normalized, right? I need to normalize, so that is equal to data test minus, I'll put a bracket. So data set test minus the mean value, that is a mu, and I want to divide this by sigma. So the test data gets us, right? So what I'll do, I'll go for the x test data once again, starting from the first data to one less than the last value. So that is normalized data test starting from 1 to this is end minus 1. Now I'll go for performing the update of the state. Okay, so there is a command called predict and update the state. So I'll show you that what it's going to do. Okay, help predict and update the state. So make the prediction on the data with the network and update the network's state. This is what you are going to do, right? There are two inputs, network and the data, and the output will be network and y. So compute the predictions of the network, right? That is net on the given data. This. So I'm trying to update. All right. So that's what I'm going to do now. So this is how it can be done. You have to use this particular function. So this is how let's okay, let me do it in this way. So the net is equal to, this is my network which already has been trained. It's predict and update the state of my net comma x, it's x tree. I want to update the state. Then this is once again I'm going to do the same data. So I'm going to get the net y predicted equal to, once again, predict and update the state using the net and the y train of the last data, which we had not considered. Okay, now you see I'm going to calculate the number of time steps for the test. test data, whatever is the length, I'll calculate that first. So that is number of testing data. Number of test is equal to NUMEL. It's a numerical length of which one? The X test. That gives this. Now, say for all of them, I have to do the prediction. Okay, so for I starting from 2 and you go all the way till the num of test. Okay, all the way from 2 till the end, do the prediction, right? Using the above mentioned this thing. So that is, sorry, this is net, comma, y predicted of first all the rows, but it is ith column. Should be equal to, use the same predict and update state of the same network. Use the y predicted of the past value, right? How do you say the past value? All the, sorry, this is all the rows and I minus 1. I minus 1 is the past value. Use the past value to get the predicted value. Okay, again we'll specify now one thing by using one thing. So that is, I want to use the GPU only for this. I don't want to use the CPU. It's going to take a lot of time. So you have to specify that execution environment, and you specify that it should be GPU. I think it should be small. All right, let's check this. Sorry, for loop should be ended. My mistake. That's why it was showing. Run this section. Whether it actually ran or not. Let's run once again. Okay, so that since it is a GPU, it ran earlier. Now I'll show you with the CPU. It's going to take slightly more time. Okay, anyway, I'm going to go back to the GPU itself. Okay, so that's done. Now the testing is over. It's actually in the normalized format, correct? So I have to bring the data back to the normal format before I plot something. So what we do here, we go for the y predicted is equal to the sigma value should be multiplied now. Previously we divided. Okay, so that is y predicted. We subtracted the new value. Now you add. So that's the predicted value. So then I'll go for the y. What is the tested data? That also I want to find out. Okay, y test is equal to I think we had a variable called data. Yeah, data test. This data test starting from second value all the way till n. Okay, now I'll calculate the root mean square error. RMSE is equal to SQRT square root. I need to take a mean of the okay y predicted minus the y tested every number needs to be raised to the power 2. Closes this and this. Okay, so then now let us run this part of the code. See, there is an error of 300. Now also let's try to plot, right? This RMS error will change as you change the length of your data, right? The training, testing, proportion, etc. As and when you change, you will get different values. Okay, right. Let's try to plot that now. So let's go for a figure. I want to plot the first. I want to plot the data, training data. Let's try to plot as it is. Okay, data train, and I want to plot all the way from 1 to end minus 1. All right, let me plot this. Then I want to hold on. Whatever machine had learned something, right? I want to plot over here on the same thing. So I hold on. Then I'll create the index. Okay, index is equal to number of training the thing all the way till number of train plus number of test. Okay, start from number of train goes till the sum of them, number of train plus test. Okay, training plus testing samples. It goes all the way till there. So now I want to plot on the same graph, plot the index, and I want to plot the data number number of the train and the y followed by I want to concatenate with the y predicted. Okay, it's a concatenation, and I want to go with dot dash format. This is a format specifier. How I want to see the graph. Okay, then hold off. X label the number of months, y label will be the number of cases, title is uh, forecasted data, then I'll go for a legend. I have two graphs plotted, right? So I can use a legend. Okay, the first one is observed data. only just observe it. Anyway, we know that it's a data. And the second one is a forecast. Right? Okay. Hopefully this runs. Right. As you can see, right, it's matching with the expected this thing, right? No, you cannot see. Just a second. I'll share it again. Right. So the red colored lines are actually they are overlapping with the blue color. That's why everything is perfect. Okay, perfectly. So that's what is the predicted data, right? So predicted data is like this, right? The previously observed data which is used for training is starting from 0 all the way till here. Okay, so till this point it is up to what is that? 398 sample we have used for training. 398 onwards up to 400, 490 something, right? 490, 480 or something, right? Okay, they were used for testing and they are actually matching, right? To the so that gives you a clear idea that how do we train, how do we use any time series data, right, for teaching the machine how to make a prediction. So this kind, it's not a classification, it is called as a regression, right? Machine is able to predict the upcoming values by observing the previous or the training values. Okay, I want you to collect some data which is a time series data other than what we have used so far, right? We may not do any other time series forecasting projects now onwards, because right, anyway, you are comfortable with the right giving the inputs and how do you give the data, etc., you know now, correct? Right. So also you can, what you can do, you can modify the data, modify the program, and by changing the testing and prediction. Normally, this is actually expected is 0.9. Let's quickly run once to see what happens. Okay, so I'll run this. 90% of the data is what I'm giving for training, not 80%. Okay, so let's see. Let's quickly see what's going to happen. Previously, the error was 300. Now I am expecting it as a lower value because I'm more training happens now. Okay, training is over. Let's proceed further. So this is the last part, and oh, now the error is more. Okay, let's see. All right. Okay, so this is what we get as a graph. Again, the prediction is like this, and the training data is like this. See here. So, like with the various, sorry, with the variation in the parameters or the hyperparameters of the CNN, right? You can get various data. You can increase the learning rate period, right? This value, right? Number of this, etc. Many things you can vary, and you can see, right, how things are going to vary. Reduce the number of layers also. Maybe that's also is a good option.